Here we study the designing of product layouts as what is called as line balancing. The goal of a product layout is to arrange workers or machines and equipment in a sequence that operation would need to be performed. The sequence is referred to as production line or assembly line or just simply as a line. These lines range from fairly short with just a few operations to long lines that have a large number of operations. Automobile assembly lines are examples of long lines. At the assembly line, for example, of Ford Mustang, a Ford Mustang would have to travel 9 miles from the start to finish. What we want to study here, the line balancing, is just the process of assigning tasks to workstations or department workstation such that they have equal requirements. The goal of line balancing is to obtain task grouping that would represent approximately equal time requirement, since this would minimize idle time along the line and would result in a high utilization of equipment and labor. Why is line balancing important? For mainly two reasons. The first is it allows us to use labor and equipment more efficiently. And second, to avoid fairness issues that would arise when one workstation must work harder than another. So this is labor and personnel consideration. Designing an assembly line. What does it mean? It means bundling tasks together, grouping tasks together such that each workstation or each group of tasks or each bundle of tasks would have equal workstation loads. So what we're looking for is fixed processing or assembly time, assembly tasks assigned to these workstations or grouping or bundling. And with the objective of balancing the line, meaning each bundle of work or each group of work have equal loads or equal load of work. And one important uh, aspects of this to consider is the cycle time, which is the maximum time available at a workstation to complete all the tasks assigned to that station. And the cycle time is the amount of time that each bundle of work is given to perform all the tasks on all the processes. Cycle time intervals are signaled in using buzzers, or the conveyor may actually that goes from one workstation or one bundle to other may actually move the product to the next workstation at a specified time. So traditionally, assembly line is fraught with difficulty bundling the task workstation in such a manner that balance would achieve. That means that they're very challenging and the challenging such as the precedence constraint. That means that when you want to bundle tasks, there might be some precedence relationship between these tasks that you have to consider. For example, you see here that scrubbing needs to be first, then rinsing, then drying. So this relationship, this sequence, a specific sequence must actually hold true. You cannot actually, for example, rinse first, then scrub, and then dry. So this actually a specific sequence or precedence relationship must hold true. So this is a condition of hold or impose on bundling task. What is wrong with unbalanced line? What will happen if we don't balance the line, assembly line? As unbalanced assembly lines are inefficient because workstations or bundling of works that you call workstation, some of them may actually have reduced workloads. So that means that if they are imbalanced, some of them they have different workload. So those that have reduced workload compared to others, they are underutilized. I mean, they have for example, idle times, and while the other workstation that are maxed out, they have to work all the time. So, and it's not fair either if you assign labor to work them at this workstation. So, but on the other hand, lines that are well balanced would operate smoothly and synchronously and efficiently and with high utilization without any significant underutilization. So the other challenge is to balance the line besides the precedence relationship between the tasks would be, for example, incompatibility, such as contamination. There might be a task or a product that when you want to process it, it might contaminate the workstation. So you might not want to do that before another important task. So another one is safety. Safety is another consideration or constraint or challenge in line and balancing the line. Or it might be that we have differences in the duration of individual tasks that may make it impossible to achieve a balanced line. So let's see an example. Here we have a precedence diagram shown here, which specifies the order of tasks that must be executed in order and the associated processing times in minutes. So for example, here you see that the first task that needs to be processed is task A with 4 minutes processing time, and task B and task C, they are right after task A with processing time of 5 minutes for B and 1 minute for C. Task D is right after B with 2 minute processing time, and task F is right after task D with 6 minutes of processing time. And task E is right after task C with 7 minute processing time. So as you see here, these tasks, in this diagram, you see the precedence relationship between these. That means that task B cannot be processed before task A or after D, F, or C or E. So this relationship must hold true. These are the constraints on the balance in the line. But on the other hand, we see that because these tasks, they have a specific time duration, if you consider each of these tasks as one station, each of them, you see that they have different load of work or here processing time. So for example, we have 6 minutes, 2 minutes, 5 minutes, 4 minutes, 1 minute, and 7 minutes. So for example, between these two tasks, C and E, there are 6 minutes difference in processing time or workload. So what we want to do is we want to bundle these tasks together in a workload or workstation such that the difference between each workstation is minimized, or what is called as balancing the line. So let's see how this would work. There are different ways that we can bundle or balance these tasks, or bundle this into different workstation. One is, for example, a two-station design. So the two-station design that you see here, what has done is it has put the task A, C, and E into one workstation, and the task B, D, and F into another workstation. So workstation 1 and workstation 2. So if you compute the processing time in each workstation, for workstation 1, that's 4 plus 1 plus 7, so that's 12 minutes. And for workstation 2, that's 5 plus 2 plus 6, which is 13 minutes. 13 minutes. So here, between these two workload of workstation, there is only 1 minute difference. So 1 minute is different is much less than the 6 minutes that we had before. Another way to bundle these tasks together is using 3 workstation design. So you see the example here, we can actually bundle task A and B into workstation 1 and task D and F into workstation 2 and task E and F into workstation 3. So in this way, the precedence diagram or precedence relationship holds true because from workstation 1 goes to workstation 2 to workstation 3. So the precedence diagram holds true. Also, if we compute the workload here for task for workstation 1, the workload is 4 minutes of processing time for A and 5 minutes for B, so that's 9 minutes. And for workstation 2, shown by blue, is 1 plus 2, so that's 3 minutes here. And for workstation, the third workstation shown by green is 6 plus 7, so that's 13 minutes. So here there is 10-minute difference between blue and green, and there is 6 minutes difference between red and blue. So here in this, the second one, the workload difference is much higher than the 2-station design. Or we could actually bundle these tasks together using a 4-station design. So that would be considering or bundling task A and C into one workstation and bundling task E into a single workstation by itself and bundling task B and D into another workstation and bundling task F into a single workstation. So this is in this scenario also the precedence diagram, the precedence relationship also holds true. But if we compute the workload, which is the total summation of the processing time of task, for the first workstation, it would be 5 minutes. For the blue workstation, it would be 7 minutes. For the B and D workstation, it would be 7 minutes. And for the last one is 6 minutes. So here the difference is smaller than the 3 workstation scenario. So as shown here, there are different ways that we can actually bundle these tasks together. But what we need to be careful about is the precedence relationship. As you see here, for all of these designs, the 2-station design, 3-station design, and 4-station design, the precedence relationships stands true. So which of these actually should we pick? Which one of these design is optimal, is the best? Before we determine or even discuss which workstation design or line balancing design is best, we need to talk about cycle time. Cycle time is the maximum time allowed or allocated at each workstation to complete the set of tasks assigned to it as one unit. To talk about cycle time, it means also to talk about output rate, because these two concepts, the cycle time and the output rate of a workstation, are interdependent. Computing one depends on knowing the other. As you can see, based on these two formulas here for cycle time is equal to the operating time per day. That's how much time you have, the working time that you have, for example, per day, 8 hours shift, for example, divided by the desired output rate. And so that means that you need to know the desired output rate to compute the cycle time. Or if you know the cycle time of a workstation, then you can compute the output rate. So the output rate would be the operating time per day, that's the how many hours of shift work you have per day, divided by the cycle time of your workstation, and that's going to give you the output rate. how the cycle time would work. So let's see an example. So here we have a set of 5 tasks here with the precedence diagram shown here, and we can see the processing time of each task. For example, task 1 has zero point 0.1 minutes, task 2 has 0.7, task 3 has 1, 0.5, and 0.2 for the other task. So we want to see how to compute the cycle time for this set of tasks here, shown in the precedence diagram. The cycle time would actually depends on how you design or the balance the workstations or the line. That means that um, how would you actually bundle these tasks together as different workstation? The cycle time would actually be bounded by two extreme cases. One extreme case is shown here is where you actually consider each task as one workstation. So, for example, the first task is one workstation and you assign a worker to work on that. And the second task is a workstation by itself and you assign a worker to work on that one. And the third, fourth, and fifth task also, they own actually a workstation. So this setting, this design of line balancing would actually gives us the minimum cycle time possible. And that would be the maximum processing time of all the tasks. And that would be actually 1. So the cycle time would be 1 minute here because of the precedence constraint or relationship here. The first task would actually takes only 0.1 minutes, but after that it's gonna have to go to the second task, which second processing, which would require 7.7 minutes, and after that it has to go to the third, which would require 1 minute, and the fourth and the fifth. So in a long run, if you see the output of this system would come out every 1 minute. So every 1 minute, if they work sequentially and continuously, every 1 minute there would be a finished product. The other extreme design is when you actually bundle all of these tasks together as one workstation and assign one labor to one operator to work on this. And this design would gives us actually the maximum cycle time possible. So the output of this design would be the processing time required would be the summation of all the processing time here. So that would be 0.1 plus 0.7 plus 1 plus 5.5 plus 0.2, which is 2.5 minutes. So if we bundle these tasks all together as just one single workstation and we assign one operator to work on this, it's going to take 2.5 minutes to complete each task. So if this workstation works continuously, every 2.5 minutes we're going to get a finished product. So the cycle time here would be anything between, depending on the design that we have. For example, these two bundled together, this bundled by itself, these two bundled together. So there are different actually scenarios and different way to bundle these tasks together. But ultimately, the cycle time would be something between 1 and 2.5 minutes. So it would be between 1 and 2.5 minutes. So the minimum or the cycle time for any design would be bounded by 1, greater than 1 or equal to 1, or less than or equal to 2.5, depending on which design you actually have.